Okay, the second problem, number 2, says Camille can swim against the current at 1.5 meters per second and with the current at 3.5 meters per second. So how fast can she swim in still water? So again, we make our table. D equals R times T. And leave enough space. And then we need to label the rows. So it's against the current and with the current. So against the current and with the current, right? So now we fill in the blocks. Camille can swim against the current, against, that's the top row, at 1.5 meters per second. So this is 1.5 meters in 1 second. And she can swim with the current at 3.5 meters in 1 second per 1 second. How fast can she swim in still water? So we have her swim speed, which we'll call S, and the current, which we'll call C. So with the current, we have her swim speed, S, plus the current. And when she's swimming against the current, we have how fast she can swim in still water, and we subtract the current because the current is pushing against us. It's making us slower. So now we have our 2 equations right across the top there, right? So we read them off. So we have 1.5 equals S minus C times 1, and 3.5 equals S plus C times 1, right? There's our 2 equations. And of course we can simplify them, right? 1.5 equals S minus C, and 3.5 equals S plus C, right? And now we have to solve. So elimination works really well here, right? Because the C's will cancel. So 1.5 plus 3.5 is 5 equals 2 times S, and the C's cancel. So we get 5 halves, or 2.5, since the question was written in decimals, equals S. So her speed in still water is 2.5, and the units for this problem were meters per second. So we would say she can swim 2.5 meters per second in still water, right? And then if the question asked us to figure out how much the current is, it wasn't asked, but we could do it just to see how. We could use that equation, right? And we could say 3.5 equals 2.5 plus C, and we get the current is 1, and then we could write the current, is 1 meter per second, right? If they asked us to do that.